In the last video, we looked at slopes of these polar curves. And now what we want to do is try to figure out how we determine what an area or an arc length is with polar coordinates. So I'll set this up in two videos here. The first will just be looking at the area of some chunk of a polar curve. As you can imagine, there'll be integral formulas for us, just as they have been in the past with rectangular functions. So what I want to do is see if I can sketch something in general here. If I have some polar curve, this is f of theta, and two angles here, alpha and beta, then the region I'm looking at, A, is really that shaded in region there. It's kind of just some chunk of this polar curve, okay? Now, in general, this curve will look all sorts of different, right? And I want to do a specific example for us. But we should be able to find the area of that region as long as f is continuous. F is continuous on the interval from alpha to beta. And we set some restrictions on alpha and beta here. We say that the difference between those two angles has to be less than 2 pi, and it's also got to be positive. Basically, we have to stay within 1 revolution of theta when we integrate. Otherwise, we'll get kind of mixed results. Basically, we can't assume that the integral will give us the correct area of the region that we're trying to look at. So there's a stipulation we should pay attention to. I just have to be careful. Okay. Then the area bounded by r equals f of theta. There's my polar function. Between the radial lines, those are the angles, alpha and beta, is the following. A equals 1/2 the integral from alpha to beta of f of theta squared d theta. So I'm not going to go through the derivation of this formula. You can find it online or in the textbook if you're curious. But if I ask you to find the area of a polar curve, you'll be given the formula and then just kind of expected to work with it. So since we know that r is defined as f of theta, or f of theta is shorthand for then r, basically our kind of nicer definition here is just plugging in r for f of theta. Okay, so we're almost always going to have r equals if we're given a polar curve. So there it is. And I want to go through an example where I use this formula to find the area of some region. Okay, so the example I want to do is I want to find the area of one petal of the rose curve. R equals 2 cosine of 3 theta. Okay, one petal of the rose curve. So I want to input a graph here. I want to drop in a graph from Desmos of this polar curve. And I want to show you kind of where that curve comes from. If I plot a couple points here. Oh, I'm sorry. Sorry. So when I go in here, there's my curve. And I have in blue there the radial lines that I'll use. And I'll also try to show you or outline where those come from. Basically, what I want to set up is just kind of a table of values. I kind of want to plot some points and show you kind of how this curve is generated, or at least some of it. I'm just going to choose a couple points here. So let's set up a table where we have theta and r, and I want to choose some specific values of theta so that when I plug them into cosine of 3 theta, I get nice results that I can use it just in my head manually. Okay, so for that, basically, since I see the 3 theta in there, I want that 3 to cancel, so I'm looking at nice values for cosine. So really kind of like minus pi over 3, minus pi over 6, 0, pi over 6, and pi over 3 are going to be nice values to use there. Sorry, I'm getting ahead. And again, that's because those 3's will cancel. When I plug in minus pi over 3, that's the same as evaluating cosine at minus pi. Now, since cosine is an even function, evaluating at pi or minus pi has no difference, right? We have to be a little bit careful. So I'm looking at cosine of minus pi or cosine of pi here, which is a minus 1, times the 2 out front should give me a minus 2. All right. Now, where does that come from? If we go minus pi over 3 for our angle there is minus pi over 3. That's negative 60 degrees. That's clockwise 60 degrees just like that. And then the radial distance should be -2. It should be through the origin to the other side 2 units. So that's why I see this point here, -2 minus pi over 3. Okay. Now, as I plot more points, basically I'm going to connect those points, but I'm going to do it with curves, curve segments as opposed to just straight lines, right? Because we aren't plotting a lot of points here, it's hard to kind of fill in the blanks, but I'm just trying to use nice points that I can do in my head. Plug in minus pi over 6 is the same cosine of 3 theta then as evaluating cosine at minus pi over 2, because 3 over 6 is a half, right? So cosine of minus pi over 2, and again, since cosine is even, that's the same as cosine of pi over 2, which would be 0. Okay, so I see this point 0. So going back then to the origin, really, right, the angle is minus pi over 6, but the radial distance is 0. So I'm at the origin then, and to get there, basically, I get this kind of curve shape in red, and I get back to the origin, just like that. Okay? Next point is when theta is 0. Cosine of 0 is 1 times 2 is 2. So an angle of 0 should put me out 2 radial units right out here. Okay? If I keep going, I keep connecting these dots, basically, these nice values I'm getting. The next one, an angle of pi over 6, takes me back to the origin. I trace back to the origin. And then finally, when theta is pi over 3, I should be at, again, -2 radial units. So back through the origin to the other side, and I land at that point there, -2 pi over 3. Okay, so the area then, I want to come up with one petal. And I've shaded the petal that I'm going to use there. Why did I choose that petal? I think it's the easiest, right? I could look at some of the other ones. The areas would, of course, be the same. But the bounds on my integral would change depending on the petal that I'm looking at, right? And I want the easiest if I can. So really, the easiest way to do this would basically be to integrate from the from the polar axis, 0, for theta, up to some value of theta to get all of a petal. Well, that's a little bit difficult here because our first petal there kind of straddles the polar axis. Okay? So we'll have to integrate a specific way here. Here's my general formula, 1/2 the integral from alpha to beta of r squared d theta. And in our example here, I see the 1/2 integral. Now, what alpha and beta will we use? Again, I've colored them in that blue dotted line. Where do I see those come up? That's those collection of points from minus pi over 6 to pi over 6. And if you go back and see how I'm tracing that petal, you'll see that I start when theta is minus pi over 6 at the origin. I go out when theta is 0 to that point on the polar axis and then back to the origin. That's one whole petal from minus pi over 6 to pi over 6. So that's the bounds that I'll use here. And hopefully what we'll be able to do is make that calculation a little bit easier. And I plug in my curve there for r is 2 cosine of 3 theta, and I'm going to square it because that's the formula. Now, hopefully, if we cut that petal in half, we'll be able to integrate from 0 on the polar axis to just pi over 6, and then maybe double it to get that region and then to get the whole petal. So I'll actually do that in my calculation. It's a little bit of an easier way to handle things. The next step I show you on the next slide here will be when I square that r there. I square 2 cosine of 3 theta. 2 squared is 4, and there's a 1/2 out front. So 4 divided by 2, that's going to give me a 2 out front from minus pi over 6 to pi over 6 of cosine squared of 3 theta. So I have to integrate this guy now. And to do that, cosine squared, I have an even power of cosine. That's my power reducing formula. So what I do is I write down that cosine squared of 3 theta is 1 plus cosine of 6 theta over 2. Okay, and I see that 6 theta because the angle doubles. That 2 out front is going to cancel with the 2 down below, and I'm left with the integral from minus pi over 6 to pi over 6 of 1 plus cosine of 6 theta d theta. Okay, now the integration here is not so bad, right? We've done this integral before, very similar ones. The bounds are what I'm going to have to deal with at the end, right? And again, it will be definitely easier if I can make one of those bounds 0. If you go back to the previous slide, I'm going to use symmetry to my advantage and integrate from 0 to pi over 6 and then double everything. So the integral from 0 to pi over 6 times 2 will be the area of one entire petal. Okay, keep the inside the same. And finally, I can take the antiderivative. Antiderivative of 1 is theta. Antiderivative of cosine of 6 theta is 1/6 sine of 6 theta. And evaluate from 0 to pi over 6. Okay? If you follow so far, plugging in pi over 6 for theta, each of those guys, I'll get 1/6 sine of just pi. And that's a number that I can crunch. It's a value I know. Minus what I get when I plug in 0 for theta. That's 1/6 sine of 0. And in fact, everything in red there will actually disappear because 0 plus 1/6 sine of 0 is 0. So all of that would be 0. On the left, plugging in pi over 6, I'll get the pi over 6, but sine of pi is also 0. So in fact, both of these expressions will entirely disappear, and I'm left with 2 times pi over 6, which should just be pi over 3 plus 0 is a pi over 3. And that's the area of just one petal. That's a squared unit there. That's units squared. And that's one petal of my rose curve. If you want all 3 petals, you of course then just multiply by 3. Okay, so coming up with the bounds there, I think, is probably the trickiest part. The integration, based on our techniques from Chapter 8, is basically mostly straightforward. The bounds or the angles are kind of the difficulty here. That's really the only example I wanted to show you with polar areas. The next video, I'll go through how to find an arc length of a polar curve. In fact, I'll just do pretty much the same curve, that rose curve, and find the length. Okay, enjoy the rest of your day. Thanks for watching.